Imagine you have three equations and three unknowns. Each equation gives you a clue, a constraint. Somewhere out there, there's a set of values that satisfies all three at once. The question is, how do you find them? Let's start with a concrete example. Here are three equations in three unknowns, x, y, and z. Finding the solution means finding the one point where all three planes intersect. Now, writing the full equations with all the x's, y's, and z's gets tedious, so instead we strip away the variables and pack just the numbers into what's called an augmented matrix. The left side holds the coefficients, the right side, separated by a line, holds the constants. Same information, much cleaner. Here's the key insight. There are three simple operations we can do to the rows of this matrix that will never change the solution. We can swap two rows, we can multiply a row by a non-zero number, and we can add a multiple of one row to another. Why do these work? Because each row represents an equation. Swapping two equations changes nothing. Scaling both sides of an equation changes nothing. And adding one equation to another gives a new, equally valid equation. Our goal is to use these operations to reshape the matrix into something called row echelon form. That means zeros below the diagonal, a staircase of leading ones stepping down to the right. Once we reach that shape, the solution practically reads itself off. Let's begin. Look at the first column. We want zeros below the top left entry, so we'll use the first row to eliminate the x terms from the second and third rows. Take row 2 and subtract 2 times row 1. The x term vanishes. Now take row 3 and subtract row 1. Again, the x term disappears. We've cleared the entire first column below the pivot. Now move to the second column. We need to eliminate the entry below the second pivot. Take row 3 and subtract 3 times row 2, and just like that, the second column is clean. Look at what we have now. Zeros below the diagonal, a nice staircase shape. This is row echelon form. The hard work is done. From here, we read the solution from the bottom up. The last row directly tells us the value of z. Plug that into the second row to get y, then plug both into the first row to get x. This process is called back substitution. And there's our answer. X equals 1, y equals 2, z equals 3. You can verify by plugging these values back into the original equations. Each one checks out. That's Gaussian elimination. You take a tangled system of equations, encode it as a matrix, then methodically use row operations to untangle it, one column at a time, until the answer reveals itself. Simple, systematic, and powerful.